Advanced Engineering Physics. Unit 1. Crystallography and autoeils characterization. Crystal structures, Bravais Lattices, and packing efficiency. In the previous topic, we learned that a crystal structure is formed by combining a space lattice with a basis. Now, we will study how these lattices are classified, the different crystal structures found in nature, and how efficiently atoms are packed inside these structures. Let us begin with crystal systems. A crystal system is a method of classifying crystals based on the shape and symmetry of their unit cells. All crystals that can be described using the same set of relationships among the unit cell edges and angles belong to the same crystal system. A unit cell is characterized by 3 edge lengths, represented by A, B, and C, and 3 interaxial angles represented by alpha, beta, and gamma. Depending on whether these lengths and angles are equal or unequal, crystals are divided into 7 crystal systems. The first system is the triclinic crystal system. This is the most general and least symmetric crystal system. In this system, all 3 edges are different from one another, and all 3 angles are also different, and none of them is 90 degrees. Therefore, the conditions are A not equal to B not equal to C, and alpha not equal to beta not equal to gamma. The second system is the monoclinic crystal system. Here also, the 3 edge lengths are unequal. However, 2 angles, alpha and gamma, are equal to 90 degrees, while beta is different from 90 degrees. Thus, the conditions are A not equal to B not equal to C, alpha equals gamma equals 90 degrees, and beta not equal to 90 degrees. The third system is the orthorhombic crystal system. In this system, the 3 edge lengths are unequal, but all 3 angles are exactly 90 degrees. Therefore, A is not equal to B, B is not equal to C, and alpha, beta, and gamma are all equal to 90 degrees. The fourth system is the tetragonal crystal system. Here 2 edges are equal, and the third is different. Thus, A equals B, but not equal to C. All 3 angles remain 90 degrees. The fifth system is the cubic crystal system, which possesses the highest degree of symmetry. In this system, all 3 edges are equal, and all 3 angles are 90 degrees. Hence, A equals B equals C, and alpha equals beta equals gamma, but they are not 90 degrees. The seventh and final system is the hexagonal crystal system. In this system, 2 edges are equal, and the third is different. The angles alpha and beta are 90 degrees, while gamma is equal to 120 degrees. Therefore, A equals B, but not equal to C. Alpha equals beta equals 90 degrees, and gamma equals 120 degrees. These 7 crystal systems provide the basic framework for understanding all crystalline materials. Now let us discuss Bravais lattices. The concept of Bravais lattices was introduced by the French physicist Auguste Bravais. He proved that there are exactly 14 distinct ways in which points can be arranged periodically in 3-dimensional space. These arrangements are known as the 14 Bravais lattices. Every crystal structure in nature, no matter how simple or complex, is based on one of these 14 lattices. To understand Bravais lattices, we need to know the different types of centering. The first type is the primitive lattice, represented by the letter P. In a primitive lattice, lattice points are located only at the 8 corners of the unit cell. Since each corner atom is shared among 8 neighboring cells, the total contribution is 1 lattice point per unit cell. The second type is the body-centered lattice, represented by the letter I. In this arrangement, lattice points are present at the 8 corners, and 1 additional lattice point is located exactly at the center of the cube. The corner atoms together contribute 1 lattice point, and the body center contributes another one. Therefore, a body-centered lattice contains 2 lattice points per unit cell. The third type is the base-centered lattice, represented by the letter F. In this case, lattice points are located at all 8 corners and at the centers of all 6 faces of the cube. The corners contribute 1 lattice point, while the 6 face-centered atoms contribute 3 more, because each face atom is shared between 2 cells. Therefore, the total number of lattice points per unit cell is 4. Combining these centering arrangements with the 7 crystal systems gives a total of 14 Bravais lattices. The cubic system has 3 Bravais lattices: simple cubic, body-centered cubic, and face-centered cubic. The tetragonal system has 2: primitive tetragonal and body-centered tetragonal. The orthorhombic system has 4: primitive, base-centered, body-centered, and face-centered. The monoclinic system has 2: primitive and base-centered. The triclinic system has only 1, which is primitive. The hexagonal system also has only 1 primitive lattice. Finally, the trigonal system has 1 rhombohedral lattice. Together, these make up the 14 Bravais lattices. Now let us study the 3 most important cubic crystal structures. The first is the simple cubic structure, commonly abbreviated as SC. In the simple cubic structure, atoms are located only at the 8 corners of the cube. Since each corner atom is shared among 8 neighboring cubes, the effective number of atoms per unit cell is 8 multiplied by 1/8, which is equal to 1. The coordination number of a simple cubic structure is 6. This means each atom has 6 nearest neighbors, 1 along each positive and negative direction of the 3 coordinate axes. The nearest neighbor distance is equal to the edge length A of the cube. Simple cubic structures are rarely found in nature because they have very poor packing efficiency. Alpha polonium is one of the few elements that crystallizes in this structure. The second structure is the body-centered cubic structure, commonly known as BCC. In this arrangement, atoms are present at the 8 corners, and 1 atom is located at the center of the cube. The 8 corner atoms together contribute 1 atom, and the central atom contributes 1 more atom. Therefore, the total number of atoms per unit cell is 2. The coordination number of the BCC structure is 8. Each atom is surrounded by 8 nearest neighboring atoms. The nearest neighbor distance is equal to √3/2 times the edge length A, which is approximately equal to 0.866 times A. Many important metals possess BCC structures. Examples include tungsten, sodium, potassium, iron at room temperature, and chromium. The third and most densely packed cubic structure is the face-centered cubic structure, abbreviated as FCC. In the FCC structure, atoms are located at the 8 corners and at the centers of all 6 faces of the cube. The corner atoms together contribute 1 atom, while the 6 face-centered atoms contribute 3 atoms because each face atom is shared between 2 neighboring cells. Thus, the total number of atoms per unit cell is 4. The coordination number of the FCC structure is 12. This means each atom is surrounded by 12 nearest neighbors, which results in excellent packing and high structural stability. The nearest neighbor distance is equal to √2/2 times the edge length A, which is approximately 0.707 times A. Many important metals crystallize in the FCC structure. Examples include copper, silver, gold, aluminum, nickel, and noble gases such as neon and argon in their solid forms. Now, let us discuss packing efficiency. Packing efficiency, also called packing factor, represents the fraction of the unit cell volume that is actually occupied by atoms. In simple words, it tells us how efficiently atoms are packed inside a crystal structure. Mathematically, packing efficiency is defined as the total volume occupied by atoms divided by the volume of the unit cell. If the crystal contains Z atoms per unit cell, and each atom is assumed to be a hard sphere of radius r, then the packing efficiency is equal to Z multiplied by the volume of one sphere divided by the volume of the unit cell. Since the volume of a sphere is 4/3πr³, we can calculate the packing efficiency for different crystal structures. For the simple cubic structure, there is 1 atom per unit cell. The atoms touch along the edge of the cube. Therefore, the edge length A is equal to 2r, where r is the atomic radius. Substituting this relation into the packing efficiency formula gives pi by 6, which is approximately equal to 0.524. Thus, only 52.4% of the available space is occupied by atoms. The remaining 47.6% is empty space. For the body-centered cubic structure, there are 2 atoms per unit cell. The atoms touch along the body diagonal of the cube. The body diagonal has a length equal to root 3 times a. This diagonal contains 4 atomic radii. Therefore, 4r is equal to root 3a. From this relation, the atomic radius becomes root 3a divided by 4. Substituting this value into the packing efficiency formula gives pi root 3 divided by 8, which is approximately equal to 0.68. Thus, the packing efficiency of BCC is 68%. This is much higher than that of the simple cubic structure. For the face-centered cubic structure, there are 4 atoms per unit cell. The atoms touch along the face diagonal of the cube. The face diagonal is equal to root 2 times a. Since the face diagonal contains 4 atomic radii, we have 4r equal to root 2a. This gives the edge length a equal to 2 root 2r. Substituting this relation into the packing efficiency formula gives pi divided by 3 root 2, which is approximately equal to 0.74. Thus, the packing efficiency of FCC is 74%. This is the maximum possible packing efficiency for identical hard spheres. Interestingly, the hexagonal close-packed structure, or HCP, also has the same packing efficiency of 74%. The difference between FCC and HCP lies only in the stacking sequence of atomic layers. In FCC, the stacking sequence is A, B, C, A, B, C, and so on. In HCP, the stacking sequence is A, B, A, B, A, B, and so on. Although the arrangements are different, both structures achieve the same maximum packing efficiency. To summarize, crystals are classified into 7 crystal systems and 14 Bravais lattices. Among cubic structures, simple cubic has the lowest packing efficiency, body-centered cubic has moderate packing efficiency, and face-centered cubic has the highest packing efficiency of 74%. Understanding these structures is essential because the mechanical, thermal, and electrical properties of materials depend strongly on how atoms are arranged inside the crystal.